All right, so now we want to talk about graph data structures. And the idea is if I have a graph, graphs are really important in computer science, have many applications. Well, how do I store it in memory? So we're going to use two different types of data structures to store graphs in memory. So we're going to have two approaches. But before we talk about that, let's first talk about how we can store a list of vertices. So let's say we have a list of vertices like this. And so there's a specific order. There's V1 and then V2 and then V3 all the way through Vn. So we have n vertices in a specific order. And we want to represent that in memory. So we can, one way to do it is to use something called a linked list, So a linked list looks like this. It's made up of a bunch of nodes that are linked together. And this is the beginning of the list, and this is the end of the list. So this is the first, if we're representing vertices, this is the first vertex, and then this is the second vertex, right? So the idea is that the order is based on starting from on the left and then following the arrows. So, well, starting from the head of the list and then following the arrows. So then V2 and then V3 and so on. And then Vn is the last vertex. And then since it's the end, it's the last vertex in the list, it doesn't point to any other vertex. So there's this slash, we put a slash through this part here, right? So V1 points to V2, V2 points to V3 and so on, but then the Vn doesn't point to anything. Okay, so that's a list. Now, how do we represent a graph? So two ways. So first way is using an adjacency list. So an adjacency list is an array of vertices where each vertex comes along with a list of the vertices that are adjacent to it. So for example, let's say we have this graph here, right? A, B, C, D, E with these edges. So this here on the right is the adjacency list for this graph. So notice we have an array of vertices. That's this table here. Well, that's this array going from top to bottom, A, B, C, D, E. So it's the array of the vertices of the graph. And then each vertex comes along with a list of the vertices that are adjacent to it. So which vertices are adjacent to A? Okay, which vertices are adjacent to A? Well, the answer is C is adjacent to A and E is adjacent to A. So we have a list C and E. Again, we have a list C and E because those are the things that are adjacent to A. Now we go on to B. Which things are adjacent to B? Well, there's only one thing adjacent to B, it's C. So we have a list of one thing. How about C? Which things are adjacent to C? Which vertices are adjacent to C? Well, we see A, we see B, and we see E. So we make a list, A, B, and E. Okay, so this list is the list of vertices that are adjacent to C. Now, D, there's nothing adjacent to D. So we don't have any list here. E, E is adjacent to A, and it's adjacent to C. So we have this list. We have this list A and C. Okay, so that's how we represent a graph using an adjacency list. The other way of representing a graph is using a matrix, and which is a table, and here it's indicating which vertices are adjacent to each other. So here, let me show you how we have to fill out the table. So A is not adjacent to A, so you put a 0 here, right? There's no edge going from A to itself, right? So like there couldn't be such a thing. We said before it's impossible. So 0. Is there an edge between A and B? No. So it's also a 0. Is there an edge between A and C? Yes. We put a 1. So the idea is 0 means false, 1 means true. Is there an edge between A and D? No. A and E? Yes. Right. There's this edge going from A to E. Okay. Then let's see. B. Which things are adjacent to B? Well, only C. C is the only thing that's adjacent to B, so we'll put a 1 there, and the rest will be zeros. Now C, which things are adjacent to C? So we see A, B, and E. Okay, so we're going to have a 1 here, a 1 here, and a 1 here, and we'll have 0, 0 here. Now D, which things are adjacent to D? Well, the answer is nothing. So we have zeros all the way down this row. What is adjacent to E? Well, it's A and C. So there's a 1 and a 1, the rest are zeros. So this is the table or the matrix that represents this graph. Again, the point of a graph is not the way it's drawn on the paper, right? The point of the graph is what are the vertices and which things are adjacent to which things, which vertex is adjacent to which vertex. So this matrix gives you all that information, or this adjacency list that also gives you all that information. Just one little thing to point out here. If you draw a line here through this matrix, it should be symmetrical. It should be symmetric about this line, right? So the rectangle, sorry, the triangle on the top right is symmetric with the triangle on the bottom left. And that makes sense because every time there's an edge between, like, x and y, between x and y, there's also an edge between y and x. So it's a symmetric type of thing. Now, how about if we have a weighted graph? Okay, so with a weighted graph, we need to store some additional, hold on, there's some little issue there. With a weighted graph, we need to store some additional information, right? So with a weighted graph, we need to store the weights. So we have vertices, and we have edges that are making vertices adjacent to each other, but we also have weights. So we have to store that information too. So for A, so let's say it's the same structure as the earlier graph, but now I added weights. So we have, again, A, B, C, D, E. This is, again, this all here is this is the adjacency list for this matrix. So we have our vertices listed out in an array, and then for each vertex we have a list of things that are adjacent to it. So what is adjacent to A? Well, C and E. And now C is adjacent to A with a weight of 3, right? Because this weight between C and A is 3. And then A is adjacent to E with a weight of 7. Okay, and the rest of the table is all the same type of idea. So notice here, each little box has 3 parts. It has the vertex, it has the weight, and then the next thing, or the slash if there's nothing more. Now, how do we do this in a table? Well, what we're going to do is, instead of putting zeros and ones, we're going to put zeros or weights. So we'll still put a 0 here. Now, A and B, there's no edge, so we'll put a 0. A and C, they are adjacent. A and C are adjacent, so we won't just put a 1, we'll put actually a 3. Okay, to indicate the weight of that edge between A and C. Then let's see, A and D, they are not adjacent. A and E, they are adjacent, and the weight is 7. Okay, then let's see, B and C B is only adjacent to C, has a weight of 5. The rest is 0. C is adjacent to A with a weight of 3. It's adjacent to it's adjacent to B with a weight of 5. It is adjacent to, why is it so hard? It's adjacent to E with a weight of 2. And then it's not adjacent to C, and it's not adjacent to D. And then let's see, D is not adjacent to anything, so that's all. It's going to be zeros. And then E is adjacent to A with a weight of 7, and then E is adjacent to C with a weight of 2, and the rest is going to be 0. So once again, this is symmetric. Okay. All right. So that's how we represent graphs in using data structures.